In the previous video, we introduced functions of two variables and looked at some of their basic algebraic properties, things like finding the domain and range and graphing them. In this video, we're going to start developing calculus for multivariable functions by starting with limits. So to get started, we have to make sense of what a limit means in the context of a multivariable function. So we'll start with two variables. So we're going to let z equal f of xy. That'll be a function with two variables. And we have a domain D, which we know is some region in the plane. And this domain needs to contain points near a point AB. Right, notice that I'm not assuming that AB is in the domain. It just needs to have points near AB. Right. So with that setup, then the limit of f of xy as xy approaches AB is going to be L, which we'll write in sort of a natural way. The limit as xy approaches AB of f of xy equals L. If the values of f of xy, that's function values, approach L, as xy approaches AB along any path in D. So it looks a lot like the definition of a limit in the other context that you've seen before. Like I'd mentioned when we talked about limits with vector functions, there is an epsilon delta definition for this if you've seen those before, and it's very similar to the ones that you've seen before in that case. But we don't need to go into that much detail. We just need to sort of know the basic idea of a limit and how that works for what we're going to be doing in this course. So we're going to skip the epsilon delta definition. However, the thing I want to really point out here is these last 5 words of this particular definition. This needs to xy needs to approach AB along any path in the domain. When we're talking about limits of functions of one variable, if we're taking a limit, let's say we're taking a limit as x goes to 4 of some function, there's really only 2 ways you can approach 4 on the real line. You can approach from the left and from the right. And so in Calculus 1, you have the right hand and left hand limits. And one of the first things you learn about limits is that if the left hand and right hand limits are both exist and they're equal, then that value is equal to the two-sided limit. So in the plane here, if we have a point AB in the plane, there's actually infinitely many ways we can approach that point in the plane. We can approach along a horizontal or vertical line. We can come in at an angled line. We could approach along a parabola or something even more than that. And so this fact that we have to approach on any path in D makes this a very strong condition. And we'll see several examples of this in shortly. But before we do this, I just want to mention that the usual limit laws, so the idea that if I have the limit of a sum and the difference of two functions, that we could write that as the sum or difference of two limits, and various limit techniques that you've seen previously from Calc 1 at the beginning of that course, these all still apply in this setting. Obviously, we might have to apply them a little bit differently because we have a different kind of function, but the rules themselves will still be valid. So let's start off with an example of a limit that exists, right? So let's say I wanted to compute the limit as xy approaches the origin, 0, 0, of the function xy minus y squared all over square root of x minus square root of y. Right, so this is the limit we want to compute. Now, if we think back to the beginning of Calculus 1, when we saw limits that involved a square root minus a square root, like in the denominator here, we had a technique that we almost always went to, and it almost always worked to simplify our function, to rewrite our function in a nice way. And that is the idea of multiplying and dividing by the conjugate of that expression. Right? So if I wanted to compute this particular limit, what I would probably do, or start by doing, it may or may not work, but we would multiply this expression in the numerator and denominator by the square root of x plus the square root of y. Right? And so in the numerator, we don't get very much simplification here. Although I will say on the original numerator, I am going to factor out a y. So our original numerator, we factor out the y, and we're going to get y times x minus y. And then that'll just multiply by the square root of x plus the square root of y. And in the denominator, when we multiply together these conjugates, we will just end up getting x minus y. And so like in Calc 1, a lot of times when we multiplied and divided by the conjugate, we had something that simplified nicely. And so in this case, that's exactly what happens. That x minus y cancels out. And so we have the limit as xy approaches 0, 0 of y square root x plus square root y. And in this case, we are able to now evaluate this function at 0, 0. The original function was not defined at the origin because the denominator would have given us a 0 minus 0, which is, of course, 0. We can't have a 0 denominator. But now we've gotten rid of the denominator. And so this function is just equal to 0 times the square root of 0 plus the square root of 0. So just we plug in 0 for x and y. And, of course, this is all equal to 0. So this particular limit of this function, as xy gets closer and closer to the origin, the z value of the function, the output of the function, is going to get closer and closer to 0. Right? So this tells us that if we were to graph this particular function, that this particular function would not be defined, the graph would not exist at the origin because the original function for the original function, we cannot evaluate it at 0, 0. However, as we get closer to the origin, we will get points on the graph that gets closer to the origin in 3 space. So if you want to try to do a similar one like this one, then you can try this one. I'll write it in blue over here. So if we want the limit as xy goes to 1, 4 of the square root of x plus 3 minus the square root of y all over x minus y plus 3. Right? So if you want to try this one, right, you can try this one, and the limit turns out to equal 1/4. So you can check yourself to make sure that you are okay with remembering how these particular limits work. Using the limit laws and various techniques like multiplying and dividing by conjugates can be used just like in Calc 1 to show that a limit exists. But to show that a limit doesn't exist, we need to do something a little bit more. So in Calc 1, if we wanted to show a limit does not exist, the standard way to do that was to compute the right and left hand limits of the particular function and get two different values. If the left hand limit was 1 and the right hand limit was 2, then certainly the two-sided limit can't exist because we approach different values. So in this case, since we want the limit to exist along from any path as we approach the point AB, in order to show the limit doesn't exist, what we need to do is we need to find two different paths in the domain on which the function f of xy approaches different values. So we have lots of options here. There's, like I said, there's infinitely many paths that you can approach. And so we'll look at a couple examples here of some different things that could happen. But in reality, if you have a limit problem and you want to solve it, you really just have to kind of pick a particular path and check the limit. And sometimes you'll check two different paths and you'll get two different values and you'll be done. And other times you'll pick two different paths and you'll get the same value, and then you'll have to pick a third path, maybe a fourth path. But the goal is to find one that doesn't, that gives you a different value than others that you've looked at. So let's look at this example. So let's say we want to compute the limit as xy approaches 0, 0 of the function x squared minus y squared over x squared plus y squared. All right, we want to find this particular limit. So the first thing we should always try with limits is try to just evaluate at the point, 0, 0 in this case. But you'll notice that in the denominator that gives us a value of 0, and so that point is not in the domain. Now you'll also notice that that is the only point not in the domain of this particular function. Any other point in the plane we can substitute into this expression, we get a real number output. And so the only point not in the domain of this function is our origin, and that'll be helpful actually. The next thing you might look at is to see if there's some kind of algebraic approach to this problem, like in our previous example, where we could do some algebra here and rewrite this function in a nice way so that we could actually compute the limit. And in this case, there's really nothing that we can do. There's obviously no square root, so the multiplying and dividing by conjugate approach will not help us. The numerator does factor as a difference of squares. It'll be x minus y and x plus y, but the denominator doesn't factor. It's a sum of two squares, which never factors. And so we can't factor and cancel anything out like that. And there's just really no nice algebraic way to approach this problem. And so what we're going to then try is to try to show that this limit doesn't exist. And so to do that, we need to find two different paths in the domain, which, like I said, includes every point except for the origin, so we can pick any two paths towards the origin, in which the function would get closer and closer to different values. And so we really just have to kind of guess on a path. Once we have some intuition about how these functions work, you might have an idea about what paths to pick. But one thing we could always start with, and one thing I always start with, is I always start with approaching along the x and y axis. So we're going to start by approaching along the x-axis. So when we do this, what we're going to get is the limit of xy as xy approaches 0, 0. And then I'm just going to put underneath this y equals 0 to indicate that we're approaching on this particular line y equals 0. That's just the x-axis. And so when y is equal to 0, our function becomes x squared minus 0 squared over x squared plus 0 squared. Right? At every point on the x-axis, y we know is 0, and so we can just substitute 0 in for y. But now the x's are still a variable, and they're changing as xy moves closer and closer to 0, 0. However, when we get rid of all of this, that doesn't matter. What we have is a function that's very simple. It's x squared over x squared. And as x gets closer and closer to 0, except never reaching that point, this gets closer and closer to that number squared over that number squared, which is always equal to 1. And so if we approach the origin along the x-axis, these function values get closer and closer to 1. And so what we now need is to find a different approach, a different path that gives us a different limiting value other than 1. And so a natural thing to then pick would be the y-axis. So we're going to approach this along the y-axis. And so now we have the limit as xy approaches 0, 0 along the line y or x equals 0. And now we have x being 0, so this is going to be 0 squared minus y squared over 0 squared plus y squared. And so this ends up, the function is negative y squared divided by y squared as xy gets closer and closer to 0. And as long as y is not 0, which it will not be in this case, we get a limiting value of negative 1. Okay. And so what we see here is that these two different paths give me two different values. Along one path, the limit looks like it should be 1. On the other path, it looks like the limit should be negative 1. And since the limit can only be a single number and we can't have two different limiting values, we're just going to say this original limit does not exist, which we'll represent just with the acronym DNE. So this particular limit does not exist. So let's look at another example. So in this example, let's take the limit as xy approaches the origin of the function xy divided by x squared plus y squared. Okay. All right, so again, we notice that the only place that this function is not defined is at the origin, so we don't have to worry about our paths going through some undefined point. We just want any path that goes to the origin. And there's no nice algebraic way to simplify this in any obvious way, so we're just going to try looking at some different paths. Right? So if we first go with the x-axis, like we did in the previous example, so we're going to compute the limit as xy approaches the origin along y equals 0. Right? This function becomes x times 0 over x squared plus 0 squared, which is just 0. Right? The numerator here doesn't matter what value x is. X times 0 is always 0, so this is always going to be 0 over x squared, which is equal to 0. So along the x-axis, this particular function will approach the value of 0. Now, we'll go ahead and do the y-axis as well, but if you notice, if you think about it just for a little bit, you'll notice the exact same thing is going to happen because of the product of x and y in the numerator. So if we approach from the line x equals 0, we're going to have 0 times y in that numerator over 0 squared plus y squared. And again, we're going to have a value of 0. Right? Now, at this point, you might think, oh, these are the same value, so that this means the limit must exist. So one thing I want to just point out here is that just because these are the same value, this does not mean the limit exists. Right? What it means is that we don't know for sure that it doesn't exist. Right? It is possible that the limit exists, but it is also possible that it doesn't exist. And so if we come up with the same value here, what this tells us is that we should try a different approach on a different path. And so we can try a different line. For example, maybe we want to try the line y equal to x. Okay. And so if we try the line y equal to x, we're going to compute the limit as xy approaches the origin along y equal x. And so if y is equal to x, then this becomes x times x over x squared plus x squared. So what we have is the function x squared divided by 2x squared. Right? And x can be in any number that's getting closer and closer to 0. And so this limit is pretty easily seen to be 1/2. And so this function approaches the same value of 0 along the x and y axis, but if we approach it along a different line like y equal x, we get a different value. Right? So here are the different values that we need. And so from these two values, or by comparing the x-axis with the line y equal x, whichever one you want to do, we can conclude that this limit does not exist, just like the previous one. Right? So the goal here, like we had said earlier, is to find two different paths, in this case the line y equal x, and either the x or the y-axis, that give us different values. Right? In this case, these are the two lines that work. So we're going to look at one more example of a limit. So we're going to compute the limit as xy approaches the origin again. Now of the function xy squared divided by x squared plus y to the 4th. So we could go about this the same way that we did the previous example. We could check the x-axis, we could check the y-axis, and if those are the same, we could check y equal x, and if that's the same, we could try a different line. But because I know how to do this problem, I'm going to kind of skip ahead, and I'm going to do all lines at the same time. So I'm going to approach along the line y equal mx. All right, so these are lines through the origin. Now the only line this is not considering is the y-axis, x equal to 0, but this is going to approach along every other line. All right, and so we want the limit as xy approaches the origin along the line y equal mx. That's an arbitrary line through the origin. Right? And so when we do this, we want to replace y with mx. So the numerator becomes x times mx squared. The denominator is x squared plus mx to the 4th power. And so we're just going to do some algebra with this particular function. So we have the limit as xy approaches the origin along y equal mx. So the numerator here, we're going to be m squared x cubed. And the denominator, we're going to have x squared plus m to the 4th times x to the 4th. Now every term in this function has a factor of x squared. So we can actually remove a factor of x squared from every term. So we just get the function m squared x divided by 1 plus m to the 4th x squared. And now notice we've removed the issue of this function being undefined at the origin. So now we can just substitute in x and y equal to 0. And of course, y, if x is 0, so is y, but we don't have a y. So we're just going to let x be 0 in this case. So this is m squared times 0 over 1 plus m to the 4th times 0 squared. So this is 0 over 1 plus 0, which is equal to 0. All right, now I only wrote the 1 plus 0 in the denominator there to point out this is not a 0 over 0 indeterminate form, but rather a defined expression 0 over a positive number 1. Right, and so this is actually sort of upsetting news to some degree because we've just approached along every line except for the y-axis, and we see that along any particular line, we will always get a limit of 0. And this includes the x-axis, the line y equal x, the line y equals 7x, and so forth. Now I won't write it down, but if you do approach this from the y-axis, all right, we're going to let x equal 0 in our original function, and you'll notice that we will get 0 as well there because we have an xy squared in that numerator. So just like kind of in the previous example, when we approach along the y-axis, we set x equal to 0, and we will get a limit of 0 as well. And so this function is actually 0. The limit has a limiting value of 0 along any line, which means if we want to show that this limit doesn't exist, we need to pick a path that is not a line. All right, so if we can't pick a line, the next sort of simplest curve would be a parabola. And so we can start by looking at the parabola x equals y squared. Right? Now you might wonder why I'm picking x equal y squared instead of the more standard y equal x squared, but this is really just based on the algebra of that particular function. I want to try to get, if I do this, you can see it when we do the substitution, we'll be able to get a very nice, function that simplifies and we can easily compute the limit. Right? So we want the limit as xy approaches 0, 0 along the parabola x equals y squared. Now when we do this, we'll replace x with y squared. So we're going to have y squared times y squared in the numerator. And we're going to have y squared quantity squared to represent x squared plus y to the 4th in the denominator. And so what we end up getting, we want the limit as xy approaches the origin along x equals y squared. And we get y to the 4th divided by y to the 4th, divided by 2y to the 4th. That's y to the 4th plus y to the 4th. And y to the 4th over 2y to the 4th is always going to equal 1/2. And so this value, along this parabola, we get a limiting value of 1/2. And so along any line, we saw that the limit was 0, but along this parabola, it's equal to 1/2. And so those two numbers being different tell us that this limit here does not exist.